Thank you very much, Ramya. So today we will explore turbidity and its implications. Take please a look at this visualization. What we see here is actually water that contains many stuff inside. Today we will talk about the particles that are inside the water. Basically, we can see, for example, rod-shaped bacteria and minerals. We can also see organic debris that are all suspended inside a fluid matrix. So today, our goal is actually to understand how this soup of particles interacts with light and why this matters for human health. We classify water into three different pillars. One of the pillars is the physical characteristics of water that relates to temperature, conductivity, odor and taste, and suspended solids. All of these are actually indicative of both the aesthetic and the physical state of water. In addition to that, water can be classified into chemical, which relates to both the organic and inorganic molecules. In addition to that, we also have biological classification, which relates to the living organisms inside the water. So today we will focus on turbidity. If we think about the types of particles that we have in water, we have living particles, which relate to bacteria, viruses, protozoa, and algae. We also have non-living particles. These mostly relate to the mineral fragments and organic particles. In addition to that, we also have inorganic particles, for example, iron oxides, and also organic macromolecules. We define particles as solid phase constituents. They actually form a suspension inside water, and the sizes of the particles can range from the nanometer range to micron range and above. One of the most important classifications are the colloids. The colloids, as we see here, colloids, those are the tiny particles. These particles do not settle naturally, and they are in the size of 1,000th of a micron to 1 micron, okay? So these are actually the tiny, small particles. In addition to that, we also have total suspended solids. The total suspended solids are particles from the size of larger than 1 micron. And we actually measure the total suspended solids by weight. When we try to analyze particles in water, it's very confusing because there are multiple methods in order to analyze particles in water. Some of the techniques provide direct visualization. Others provide computational evidence of particles' physical state. For example, optical and imaging, which can be analyzed by microscopy. This is the gold standard to obtain actually high resolution identification. We can use, for example, scanning electron microscopy and transmission electron microscopy. They allow us to actually view the size, shape, and morphology of the particles, but we can also use, for example, microflow imaging, which provide us an automated size, counting, and morphology of the particles. In addition to that, we can use light scattering techniques. So rather than viewing the particles directly, we can actually indirectly obtain a characterization of the particles by interferences with incident light beam. For example, we can use dynamic light scattering, which provides us nanoparticle size range, or laser diffraction, which allows us a wider range of size distribution from the micron to the millimeter range. In addition to that, which is the topic of today's lecture, we can use light scattering in order to obtain the bulk particle concentration using a parameter that is called NTU, which we will soon study about it. So the other methods actually focus on providing the individual particle characteristics, but turbidity allows us to obtain the bulk particle characterization. In addition to that, we also have additional methods such as electrical methods and also chemical and compositional methods and gravimetric methods, which provide us the total suspended solids. I would like to show you a short video on using microflow imaging for particle analysis by using a camera that captures millions of particles and provides both the size and the shape of the particles. In addition to that, it provides additional parameters, which we will not talk today in the lecture, but it also provides parameters, for example, the ferrodiameter and the intensity, which allows us an indication of how much light can pass through the particles. And when we see here this image, we can actually see both the beauty and the complexity of particles. We can see, for example, here microbes, which are suspended in particles in water, but also we can see aggregates, which are actually an aggregation of particles. We can see also some type of nanoparticle. We can see also clay particles. We can see, for example, silver nanoparticles attached to a bacteria. Therefore, as we can see, particles are both beautiful and complex.
Hi everybody, my name is Ronnie. I'm a PhD student under the supervision of Professor Adas Maman. I want to show you this MFI 5200. This is a microflow image analysis system. The particle size of the MFI 5200 is between 1 to 100 microns, but the best reliability and accuracy is between 2 to 70 microns. I would like to demonstrate how the system works. First, we initialize the system by pressing the turn on button on the back. Then we can see the blue light flashing.
methods are very complex. It's very difficult to measure particles in water using all these methods, such as light scattering and light blockage and image analysis. Although they provide us more precise data and information on the particles in water, and we can also obtain a particle size distribution. In addition to that, some of the methods can also provide us the shape of the particles. But it's really complex to think, how can we actually use these methods to measure particles in water? When we know that water quality standards are actually looking at quick analysis of the water in order to understand if the water is safe or not. Therefore, these methods, although they are good for many applications, for water quality analysis and standards, they are problematic. And therefore, we are using aggregate characteristics in order to obtain particles in water. So what is an aggregate characteristic? An aggregate characteristic will provide us one number per water type and will not provide us the individual constituents or the individual particles in the water. It will provide us a measured value that will indicate the quality of the water. We have actually two types of aggregate parameters that provide us information on the water. One of them is total suspended solids, which provide us the weight of the particles. Basically, what we do, we take the water sample, we filter it on a filter, we dry the water, we weight the particles on the filter, and we obtain the amount of milligrams of particles per milliliter of water. So this is one type that provides us one number per water quality. The other type of method is called turbidity, which is actually the topic of the lecture today. So what is turbidity? Turbidity is an optical property, and it causes light to be scattered and absorbed rather than transmitted. So basically, if we think about it, definitely we need a light source. We also need a sensor to measure the scattered light. So the scattered light sensor is located 90 degrees to the light source. If we see in the image below, we can see the light source, and we can see actually here the sensor that measures the scattered light at a degree of 90 degrees to the light source. Turbidity will increase as the intensity of the scattered light will increase, and it's expressed in a parameter that is called NTU, which is nephelometric turbidity units. Here we will see a video that provides us background on what is actually turbidity and seeing the unseen.
All right, let's talk about water. We all know what clean water looks like, right? It's clear, but what about when it's not? What's really going on when water gets cloudy? Well, it turns out the answer is pretty fascinating, and it's a huge deal for keeping us all safe. So let's start with a really basic question. When you look at a glass of murky water or a muddy river, what are you actually seeing in there? People have been wondering about this for a long, long time. We've all been there, right? You get a big downpour, and the next day, that creek that was crystal clear is now this murky brown color. It's such a common sight, but it means something really dramatic has happened inside that water. So what is all that stuff? Is it just dirt? Or is there something more complicated floating around in there, blocking out the light and giving it that cloudy look? You know, what you're seeing here is it's a really cool piece of history. On the left, that's what people back in the 1840s thought was swimming around in a single drop of water. They called them animalculae, and they looked absolutely terrifying. And while our modern view on the right is a little less monstrous, it kind of proves their point. Water is just teeming with invisible stuff. And that brings us to what you could call the invisible particle problem. Because all those tiny things, the ones that are way too small for us to see one by one, they add up to have a huge, huge impact. See, that cloudiness isn't just one thing. It's this complex soup of tiny particles all suspended in the water. You've got non-living stuff like silt and clay, but you also have living things like algae, bacteria, even viruses. They're all just hanging out in there too light to sink to the bottom. So why do we even care? I mean, who cares if the water is a little cloudy? Well, it's actually a huge deal. It's not just about how it looks. Those little particles can actually carry dangerous stuff with them. And worse, they act like tiny little bodyguards for germs, shielding them from the disinfectants we use to clean our water. They can clog up farm equipment and completely mess up the balance of a river or a lake. So yeah, this is about way more than just appearances. Okay, so if these particles are a problem, how in the world do we measure them? It's not like you can just count them. The solution is actually really elegant, and it's all about how light behaves in water. The key idea here has a bit of a sciencey name. It's called turbidity. But don't let the word scare you. All it means is that we're not trying to count the particles themselves. Instead, we're measuring their effect, the cloudiness they create. It's a really smart workaround. And this is basically how it works. A special meter shines a beam of light through a sample of water. Now, if there's stuff in the water, that light is going to hit those particles and scatter all over the place. By measuring how much light gets scattered, we can get a really precise number for how cloudy that water is. It really comes down to this simple difference. In super clear water, that beam of light just zips right through. But in turbid water, with all those particles, it's like a pinball machine. The light bounces off everything and scatters everywhere. The more stuff in the water, the more the light scatters. Simple as that. So we've got the theory down. Now let's see how this actually works in the real world. How do we turn this cool idea about scattered light into a simple, reliable test that people use every single day? The test itself is way easier than you might think. You start with a little gadget called a turbidity meter. First, you give it a baseline reading with perfectly pure water just to make sure it's accurate. Then, you take a little glass vial, rinse it out with your sample water, fill it up, and pop it into the meter. You hit one button, and that's it. The machine does the rest. Okay, first up is our baseline. For that perfectly pure deionized water, we get a reading of 0.00 NTU. That NTU stands for a mouthful, nephelometric turbidity units, but all you need to know is that 0 means 0. No particles, no scattering. A perfect score. And now, for our actual sample. The meter gives us a reading of 2.69 NTU. Okay, so it's not 0. That tells us right away there's something in there scattering the light. Just to give you some perspective, really good drinking water is usually below 1 NTU. A muddy river might be over 100. So 2.69 tells us something is definitely going on. We have our number. So we have a number, 2.69. And it's so much more than just a number on a screen. That single number tells a really important story about what's happening in that water. That number is basically a vital sign for the water. If you're running a water treatment plant, a low number tells you your filters are doing their job. But if that number suddenly spikes, that's your first alarm bell. It could mean there's a contamination problem or a system failure, and it lets you fix it before it becomes a real danger. And really, when you get right down to it, this super simple test is one of the cornerstones of public health. It's used all day, every day in plants that provide our drinking water and in facilities that clean our wastewater before it goes back into the environment. It keeps us and our ecosystems safe. So just by measuring how light scatters, we get one little number that helps protect billions of people.
Okay, so what we saw actually is an indication of what turbidity is and how important it is for public health. But beyond understanding this, we also need to understand a little bit about the physics of turbidity and also to differentiate that from absorbance. So here, for example, we have a case of a lamp, and we have our water sample that contains particles. Now, when light hits those particles, we have two options. One of them is to measure turbidity, which is the scattering of light at 90 degrees angle. The other one is to measure absorbance or transmittance, which is inline photodetector for measuring these parameters. Now, absorbance relates to the dissolved constituents in water that absorb the light. For example, humic matter or natural organic matter all these compounds can absorb the light. Turbidity is not caused by dissolved constituents. It's only caused by particles in water, and mainly by small particles, as we will see soon. So a water that is perfectly transparent will have zero absorbance and 100% transmittance. Now, if we do not account for the water absorbance in the turbidity measurement, we will have an artifact. And that's why it's really important to place the photodetector at a degree of 90% in order to allow us to a degree of 90 degrees in order to allow us the light scattering, measuring the light scattering of particles. And if we look at this equation is the attenuation of light in a medium. And this is the sum of the light absorbed and also the light scattered. So therefore, it's important to actually look only at the light that is scattered and not consider the light that is absorbed when we want to measure light scattering by particles. In addition to that, light scattering by particles is also size dependent, which means when D is the size of the particle, when the size of the particle is much smaller than the light wavelength, which means small diameter particles, for example, a particle that is 0.05 micrometer in size, it will scatter light uniformly across all directions, as we can see here in this image. But when D, which is the diameter of the particle, increases relative to the wavelength of light, then in this case, we have large diameter particles, for example, particles at the size of 5 micrometer, and they will exhibit, as we can see in this image, primarily forward scattering. Therefore, it's very important to understand if the particle is smaller than the wavelength, or if it is in the size similar to the wavelength or even larger. And that will impact the scattering patterns, and obviously it will impact the turbidity. The next slide will show us the impact of wavelength on light intensity. So the intensity of scattered light varies with the wavelength of incident light. For example, blue light, which has a wavelength of about between 400 and something, 450, 495 nanometer, will scatter light more than red light, which has a wavelength of about 600 to 700 nanometer. Now let's look at this equation here. So when the wavelength of light is smaller, obviously we'll have more scattering. And when the wavelength of light is larger, we will have less intensity. And therefore, turbidity is also sensitive to the particles in the size range of the incident light wavelength, and smaller particles will scatter shorter wavelengths more intensely. And this is actually what happens during sunset. So we all know and see the beautiful image and physics of the sunset. And because blue light is scattered away by the atmospheric thick path, that will allow the red light to reach our eyes. And we can see here also in this scheme here that the blue light is scattered while the red light will reach ground in our view. Turbidity is measured by NTU units, which is nephelometric turbidity units. And nephelometers measure the intensity of the scattered light 90 degrees to the direction of incident light. So by comparing the scattered light intensity to a standard or reference or calibration curve, we can determine the concentration of the particles. The WHO, which is the World Health Organization standards, is smaller than 1 NTU. Therefore, water that is drinkable is supposed to have smaller than 1 NTU of particles. And we can see here, for example, in this image here, a standard that has 10 NTU and a standard that has 4,000 NTU. The water is supposed to be less than 10, and basically in many countries, also the standards are even less than half NTU of turbidity units in the water. We can measure turbidity using different instrumentations, but all the different turbidity meters have three main components. One of them is the light source, the other one is the sample container, and the third one is the photodetector. So all turbidity units must have all these three components within them. So let's start to look at the light source. We can have multiple types of light sources. One of the light sources could be, for example, tungsten filament lamps. And as you can see here with the spectral image of this lamp, we can see that it's polychromatic. What does it mean, polychromatic? Polychromatic means that it emits light over a wide range of wavelengths. Now, this could be good in some cases, but it can cause interferences when we have natural colors in water, for example, organic matter, humics, fulvics, that can absorb some of the light. And this is only also highly dependent on stable voltage, and it can be subject to burnout. So this is one type of light source, which is called tungsten filament lamps. Another type of light source are narrow wavelength lights. And these are, for examples, we can see here LEDs, which is light emitting diodes. And we can see that they have a relatively narrow wavelength emission. And in this case, they eliminate the interferences, for example, that we saw in tungsten type of lamps, but they're also less sensitive to small particles. Therefore, we have advantages and disadvantages with every light source. One very important thing when we measure turbidity is the sample container. Now, each company and each instrument has a specific bottle where we measure turbidity, and it also has turbidity standard vials. We have both benchtop and portable turbidimeters, and we use, usually for them, we use glass cuvettes, as we can see in this image here, in order to hold the sample for measurements. We also have online devices that measure turbidity, and they actually measure turbidity by allowing the sample of liquid to flow through a chamber that is situated between the light source and the photodetectors. Of course, online devices are relevant, for example, for water treatment plants, effluent treatment plants, and the benchtop is mostly relevant for the lab, and portable are relevant for field tests. When we look at the photodetector, it has a very important objective within the turbidity meter. So the photodetector will convert light into electrical signal, and the output of the photodetector is proportional to the light intensity. What we learned is that the photodetector is 90 degrees to the light source, but we have also advanced turbidity meters that can also sense the back and the front scattered light, and also that transmitted radiation and the forward scattered detection. So we can also measure the back, the forward, the 90 degrees detector, and also transmitted light detector. And the output would be a mathematically combined value that provides us the turbidity meters. But most of the simple turbidity meters only provide the 90-degree detector. As we said before, the types of turbidity meters are both process turbidity meters that allow us continuous monitoring for both water and wastewater. We have the benchtop ones that are mostly in the lab, that they provide us ultra accurate measurements of turbidity. And then the portable ones, which you will take to the field, that allow us to obtain rapid tests of turbidity of the water. When we measure turbidity, it's very important to take the container and allow the water to overflow and then immediately cap the sample so we'll have no head space. We start the analysis as soon as possible to prevent any changes from, for example, temperature changes or other types of changes. And obviously, we don't touch and scratch the glass. And we clean the sample with a special cloth to remove dirt. We can also calibrate the turbidity meter using RFID vials. These are vials that have embedded radio frequency identification tags. And these are tiny electric devices that store and transmit the data wireless. These instruments receive the value, the lot number, the expiration date, and a certificate from the RFID vials. So what are the different applications? Lab bench, portable, and flow. And if we look at this infographics that summarizes everything that we spoke about now, we have first the proper sample collection, which is very critical. Then we need to calibrate the system. After we calibrate, we measure the system, and we have different types. The process turbidity meter is mostly relevant between 0 to 700 NTU. The portable one will be relevant up to about 1000 NTU. And the benchtop, which is the gold standard of turbidity meters, can even measure up to 10,000 turbidity NTU values. So why do we care about all this? Why do we care about the turbidity value of water? And again, please remember that the turbidity is actually an indication of the particles in water, but it mostly provides an indication of light scattering by particles. And if we take the water sample and measure the particles using the different particle size distributions analyzers, we will obtain different values. But turbidity gives us a very good indication of the particle content of the water, but it's not perfect. The particles, we care about particles in water because they can pose health risks. Particles can be toxic. Particles can absorb heavy metals, for example, and they can travel far. So the fate and transport of particles in water is very complex to understand. In addition to that, particles can aggregate with microbes and shield those microbes from disinfection. Also, the colloids, which are very small particles, according to Stokes' law, will not settle down, which means that these particles their fate and transport of the small particles would be different than larger particles that can settle down. In addition to that, they can inform antibiotic resistance. And we also have a new class of particles, which are called engineered nanoparticles, that also raise some type of concerns. And it is also known that everything we manufacture synthetically, at the end, we can find them in our water sources. So can we find also those engineered nanoparticles in our water? This is also a question that we need to address. But obviously, as I showed before, the particles, the size of the colloids are from 1,000th of a micron to about 1 micron. It's a huge range. And within this range, we have many types of particles, organic, inorganic. We have biological particles and non-biological particles. And therefore, the complexity, and as we saw before, the complexity and the beauty of particles is something that is very complex. And due to all this complexity, turbidity measurement provides us a very simple way to indicate on the particle content within water. In addition to that, in light of water scarcity, reuse of wastewater is becoming more and more prevalent. However, when we irrigate our fields with reused effluent water, these particles can actually clog also drip irrigation systems, especially the oxides. And therefore, it's really important to understand which particles, or if we have particles in the water and its content. So I'd like to show you a few examples on how particles interact with different types of water treatment technologies. One of them, for example, is the interaction of particles with ozone. Here we can see that we have 3 different types of micropollutants, iopamidol, iohexol, and iopramide. And we can see here that the green bar represents non-filtered effluent, while the blue bar represents the most filtered effluent. And what we can see here is that the percent degradation by ozone is much smaller for the non-filtered effluent, which means that if we want to improve degradation of micropollutants in water, it's important to filter the water before that to remove the small particles. But in addition to that, it's also very important to remember that the particles can interact also with the ozone. And that may induce either dissolution or aggregation. And that will impact the available ozone and hydroxyl radicals that are available for degradation of the micropollutants. So this is one example. Another example is the impact of particles on UV disinfection. So particles, and here we can see a particle, and this is the UV light. The light can interact with the particle and result in reflection, refraction, scattering, or the particle, for example, may be organic, and therefore the light may be absorbed on the particle. And we can see here, for example, that the particle shields the light from the bacteria, which means that the bacteria within the path length of the light will not be inactivated. So this bacteria is safe from inactivation, while the bottom bacteria will, the bottom bacteria will be inactivated, while the middle one will be not inactivated. In addition to that, in wastewater effluents, where we induce flocculation of particles, the particles will flocculate with the microbes. And what we see here with the dose response curve, initially we see a linear inactivation curve, and then we obtain tailing. Tailing means that even if we increase the UV dose, the bacteria will not be disinfected. And that is because they are protected within an aggregate. And these 2 examples actually show that there is an interaction between particles and microbes in water, or particles with micropollutants, or particles with ozone, particles with filtration, and all the different types of of water treatment technologies. And another also important comment is that most of the papers actually they take a water sample, they filter the water, and then they examine, for example, the breakdown of micropollutants in water or trace organic compounds. But use this content from the water, we don't obtain the real technology efficiency. And therefore, it's very important to understand how particles impact our water and the water treatment processes. Now, it's also very important to understand that we have a new class of particles in water, and this is the new guy on the block. Actually, it's not so new. We have also natural nanomaterials, such as different types of oxides, but we also have engineered nanoparticles. And those engineered nanoparticles, such as inorganic non-metallic nanomaterials, carbon-based nanomaterials, metal nanomaterials, or organic polymeric materials, all these nanoparticles, which are in a size of between 1 to 100 nanometer, can also be present in our water. And we also need to think about these synthetic nanoparticles that we manufacture. At the end, they will be in our environment. And it's really important to understand a few things. Are they toxic? Do they absorb to natural organic matter? And all these different interactions of particles with water are critical. Now, we would like to please scan the QR code, and we will move to the Mentimeter questions. Okay, so hopefully you scanned this, and we will go to the different.
Professor, can you show this QR code once again?
Please scan the QR code.
Yeah. Please do it quickly. All done? We can move, Professor. Thank you.
Thank you very much. Thank you very much. Okay. So let's go to the first question. Okay, so I see that most of you have responded and responded correctly. Colloids are very small particles in water, and their size is between 1,000th of a micron to 1 micron. Below 1,000th of a micron, we have the dissolved constituents. So good work, and most of you answered correctly. Excellent. Okay, so let's go to the next question. Okay. Most of you answered correctly. Excellent. It's very important. It's not only important, but it's critical to position the detector at 90 degrees because this is actually the definition of turbidity. Perfect. Thank you very much. Let's go to the next question. Okay. So the way that light scatters depends on the ratio of the particle diameter, right, to the wavelength. And Rayleigh scattering relates to small particles that scatter light uniformly in all directions, while large particles, which is my scattering, mainly exhibit forward scattering. So thank you very much. You answered correctly, most of you. And the right answer is large particles exhibit primarily forward scattering. And the next questions at the end. When you hear the word turbidity, what comes into your mind? Now be spontaneous, okay? Just answer what comes into your mind. Okay, so what we can see here is that you listened excellent to the lecture because the first word that came in most of your minds was scattering. Exactly. Turbidity is light scattering by particles. Also, you presented another word, which is cloudiness, because we know that if we go to water after flooding, or for example, when we mix water with particles, the water can look cloudy. So cloudiness is also another word that can represent this scattering. Um, I also see colloidal particles, turbidity. There are also many other interesting terms. Some of them I cannot read, but I also see muddy water in floods, cloudiness, colloids, suspended particles, purification, pollutants, polluted water, unclear water, big particles, thick water, cloudiness, as we said before. Amazing, wonderful. And you gave here many things that came into your mind. And this is excellent. So we'll stop the Mentimeter now. And thank you for providing all these different terms that came in your mind when you thought about turbidity.
Do you have any questions in class? Anyone? You can please raise your hand. I'll come to you with the mic. Okay, it's all crystal clear, Professor. Thank you so much for your wonderful talk. And if there are any questions, I'll forward them to you, Professor. Thank you so much.
Thank you very much. And I'll be happy to answer any question that comes into your mind, even if it comes later. So thank you. Thank you, Remia. Thank you.
Yeah. Thank you. Thank you for a wonderful lecture, Professor. See you in your next class.
Thank you.
Thank you.
Bye-bye.